Stripping down science. The Naked Scientists.
Hello and welcome to this week's edition of The Naked Scientists with me, Chris Smith, and also with Helen Scales. Hi, Helen.
Hi, Chris.
Now, coming up this week, how the unusual combination of archery and fishing can actually go hand in hand. And also, just because they're black and white doesn't mean that pandas can't see in colour. That's according to new research we'll be talking about later. And also, a dragonfly that's 1 metre long. Stay tuned to find out about that. Helen.
Also, this week we're focusing on the science of sight and how eyes work and how they can go wrong. We'll be talking to consultant ophthalmologist Nick Sarkis from Adam Brooks Hospital here in Cambridge and vision researcher Ron Douglas from City University in London. So if you have any questions for them, do give us a phone, email or text. Keep listening, we'll give you the numbers shortly.
And if you're in an experimental mood this week, in kitchen science, Derek's going to be looking at the science of how balls bounce and spin. It's very easy. If you want to take part, what you're going to need is a very bouncy ball. A squash ball will do, but the bouncier the better, basically, he tells me. You'll also need a kitchen work surface or some kind of surface with a tiled wall behind it. You'll also need some cooking oil or some Vaseline. And if you do the experiment correctly and you're the first through with the correct observation and explanation, you could win yourself an amazing electronics kit, and I'll be telling you more about that shortly.
And another way to win is to give our go at our teaser. Last week we asked you, where in the home would you find acetic acid? And Steve got the answer right. He said you find it in a bottle of vinegar. Balsamic, doesn't matter what kind, just some kind of vinegar.
Now this week, if you want to have a go at winning 2 copies of my book, Naked Science, I'll sign them for you, which means they treble in value and you can flog it on eBay. All we want you to do is to phone in with the answer to this. What metallic chemical do we need in our diets to make sure that we have enough red blood cells?
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Now, Helen, I saw this and thought of you this week because it's about fish. I mean that in the nicest possible way,
Chris.
being the marine biologist on our team. But scientists in Germany, a guy called Thomas Schlegel, has been looking at archer fish, and these are the fish that fire a jet of water to knock things off of plants adjacent to their pond, and then the insect tumbles into the water and they eat it. And what they did was to set up a camera which is capable of taking 5,000 pictures every single second to work out exactly how much water these archer fish are shooting. It's very clever because what it turns out they do is to tailor the amount of water that they shoot directly to the size of the target. So in other words, the bigger the target is, the more water they fire out to knock it off. And it's not something they learn to do, because what the researchers did was to grow these fish from when they were tiny babies in a tank, where they never had to actually learn to do this, because whenever the fish just shot any old amount of water, even if they missed a target, they fed them anyway. And then when they put them in the real world environment and watched them, they still knew how to directly tailor how much water to shoot out to knock something off. And so why is this important? Well, it actually uses a lot of energy to fire this water. In fact, if a fish tries to fire a lot of water to knock off a big something very large into their lake, they can burn off 30% more calories. So by saving energy, they make themselves much more efficient, so they make the most of their meal times, I suppose you could say.
Excellent stuff. Yes, we're talking about sight today on The Naked Scientists, and I have a story here about giant pandas. Now, even though they're black and white, it doesn't necessarily mean that they don't have colour vision, because this week we have news from scientists in America who've discovered that giant pandas can distinguish colours from greys. So Angela Keeling, a graduate researcher from the Georgia Institute of Technology, worked with Yang Yang and Lun Lun, a couple of giant pandas that live in Zoo Atlanta, and she found that they were able to distinguish colours from various shades of grey. Now, to find this out, she conducted a 2-year study in which she presented the 2 pandas with 3 PVC pipes, each hung underneath a sheet of paper. 2 of the pipes were hung underneath grey paper, and the 3rd one was underneath a coloured piece of paper, either red, green or blue. Now, if the panda pushed against the pipe underneath the coloured paper, it received some food, a nice tasty reward. But if it pushed one of the grey pipes underneath the grey paper, they got nothing at all. And so she repeated these tests over and over for a couple of years, whenever the pandas were hungry, presumably, and with different colour combinations, and basically found that the pandas were able to distinguish the coloured paper from the grey shades, because once they'd learnt that the coloured paper meant food, they pushed those coloured paper pipes much more often than the grey ones. We still don't really know much about the type of colour vision that pandas have, and this study, it's not clear whether they can tell between red and green and blue, but just between those colours and grey. But we now know that they can tell the difference, and it might help them perhaps in their daily, what they spend most of their day doing, which is eating bamboo, that lovely green bits of juicy bamboo. They might be able to tell where they are.
I was going to say, because obviously there has to be a reason why something wants to do something. And I don't know where the myth actually comes from that dogs, say, can't see colours, because they clearly can see colours. But we'll definitely have to get on to Ron Douglas about this later, because I know he works on this kind of thing. But I think it stands to reason that pandas would be able to see colours, because surely there must be things in the environment which, if they couldn't appreciate them, they wouldn't be able to see the danger signals, for example.
Yeah, I mean, so obviously I think there's important things in a panda's life that will help them out if they can see colours, so yeah.
Now, be grateful you weren't buzzing around literally about 300 million years ago, because you might have been in the same world as a dragonfly, about 3 feet, that's a metre long. And what scientists have done is to say, well, why is it that in the old days you had these massive great insects buzzing around, a metre-long dragonfly, it's huge, but you don't see them anymore? Why should that be? And so to find out, a researcher called Alexander Kaiser, who works over in Arizona's Midwestern University, decided to X-ray some insects. And he used a group of beetles as study subjects, because there are some obviously very small beetles, right up some very large ones. And by X-raying them, he was able to monitor how big certain structures in the beetles are. And the structures he was specifically interested in are things called the tracheoles. Now, insects don't have lungs like we do. Well, they have a tiny air passages along the sides of their bodies. And when they pump their abdomen, if you've seen an insect, it'll be literally moving its abdomen up and down. And what it's doing is working like a set of bellows, and it's drawing air in and out of its body, and with it oxygen. And it pushes it down these tiny pathways, and then it gets into the contact with the tissues of the insect, which it gives up the oxygen to, so the insect can do things. Now, when they looked at the different sizes of these passageways using the X-rays of these different beetle sizes, what they found was that as the beetles got bigger, the sizes of these pathways got bigger too, but they got bigger 20% larger than you would predict on the basis of how much the insect was growing. So these tubes had to be much bigger than the insect. You would think the insect would need them to be. Now, that's not a problem until you get to the bit where the legs meet the body, because at that stage there's an anatomical reason why these things can only become so big before they can't get any larger. So that means you constrain how big insects can be these days, because you can't get any bigger than the certain threshold size they found. And their predictions suggested you shouldn't be able to find an insect bigger than about 17 centimetres long. Now, that does actually work, because there is an insect in South America called the Titanic longhorn, which is 17 centimetres to 15, 17 centimetres in length. Now, what does this mean in terms of today and 300 million years ago? Well, today, of course, the air contains about 21% oxygen. 300 million years ago, there was much more oxygen in the environment. It was about 35% oxygen. So you didn't need these tubes to be so big in the old days. So, as a result, you could get much bigger insects, and just by doing the same breathing movements, they would get much more oxygen into their bodies. So you ended up with dragonflies that could buzz around and be 3 foot across.
It was the size of helicopters. The tracheole thing in insects reminds me of... Have you seen the film Ants, the cartoon a couple of years ago? And I think right at the end, one of the ants gives the other ant the kiss of life. And I thought, nah, that don't work at all. You have to go through all the little tracheoles down the side, not through the mouth. Right, OK. One last story from me will be... extreme environmental changes that will shape fish appearance. Yep, sorry, back to fish again. This is the devil's hole pupfish, which I will talk to you about quickly. It was one of the most endangered species of fish in the world, because the entire species lives in one single rocky pool in Death Valley in California. Now, scientists have discovered that the devil's hole pupfish, the little inch-long fish, looks the way it does, partly because of their tiny, cramped conditions. A few years ago, some of these pupfish were transferred into captivity to try and ensure that they don't go extinct if the population in the devil's hole perhaps dries up and dies out. But these pupfish bred in captivity have begun to look very different from their wild brothers and sisters. They have deeper bodies and smaller heads. And this change in appearance of the captive bred fish raises a serious question about how this rare species could be protected from extinction.
But why do they change their appearance?
We think basically it's because of the availability of food and also something to do with temperature. We know this because these researchers from the University of California in Davis have set about looking at what these changes might be, and they've taken another species that's not as threatened as the devil's hole pupfish. It's called the Amargosa pupfish, but it's quite similar. And they mimic the conditions of the devil's hole by warming up the water, restricting the amount of food these fish could have, and lo and behold, they started looking much more like the devil's hole pupfish.
So what are the implications for trying to conserve rare things like this?
Well, yes, I mean, on the positive side, I think these studies suggest that the fish might be more adaptable to changing conditions than we thought before. But it could mean that this captive bred pupfish could die if we were to reintroduce them back into the Devil's Hole in Death Valley to try and rebuild that wild population. And it also raises a slightly philosophical question about if the way an animal looks is so intimately linked to its environment, then is it still the same fish if it's not preserved in the same habitat? So does keeping Devil's Hole pupfish alive in captivity really mean anything at all if there are none left in the wild?
It's got quite wide ramifications, hasn't it? Thanks, Helen. It's The Naked Scientists, Chris and Helen, and this, coming up shortly this week, we'll be talking with Ron Douglas and also Nick Sarkis about the science of sight. So if you have any questions for us about that, we'll put them to them shortly. Our teaser this week, and up for grabs, donated kindly by noisemakers.org.uk, a group of scientists who like to make a noise about science, is an electronics kit. And what we need you to do to try and win it is to answer this simple question: what metallic chemical do we need in our diets to make sure we have enough red blood cells?
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
OK, now it's time for Kitchen Science, and this week we're off to Norwich School in Norfolk, where Derek's waiting with Martin and James and Hugh Hunt to show you the science behind bouncing balls. Hi, Derek.
Hello there. Welcome this week to Norwich School, where we've come to do some fantastic science with Hugh Hunt, basically, who's come down to do some science with us. So, Hugh, just very briefly, what is it we're going to be looking at today? Just what principle are we going to be looking at?
Well, we're going to be doing some things with a rolling ball. We're going to roll the ball towards a wall and watch it bounce off. And we have to think about how it is that in the bounce, the spin direction has to change as well as the rolling direction.
Fantastic. OK, thanks, Hugh. And also we've got two helpers here from Norwich School who's come to kind of help us out and do the experiment, tell us what happens and so on. So, guys, can you tell me your names and what years you're in, please?
I'm Martin and I'm in Year 8.
And I'm James, I'm in Year 8.
OK, nice to have you with us, guys. So, quickly, can I just find out, before we do some science, do you guys actually like science? What do you like, Martin?
Well, I like burning magnesium.
All right, and is this something you do in your spare time?
Not really, because magnesium is quite hard to get your hands on.
OK, and you would know about that. OK, that's excellent. Thank you. And James, what about you?
Well, I just find the whole principle fun and everything about it, like the different materials and burning them and doing everything like that.
OK, thank you very much. And I'm going to run through, firstly, what you need at home, because all of this can be done at home very, very easily. So then, what you need, firstly, is some kind of rubber bouncy ball. OK, just like the normal bouncy balls that you have at home. That's great. Hugh's just bouncing one there to make it clear. Also, if you have a squash ball, that's fine. That's also kind of rubber and quite bouncy, but the bouncier the better. And also, a golf ball kind of won't do, just in case you want to try that. Now then, also, you need kind of the right sort of situation, OK, and that is that a kitchen counter is good. And if that counter kind of meets the wall, OK, and the wall goes up at a direct right angle from the counter, going up vertically with no kind of skirting board or anything, then that's great. And also, the smoother the better. So just look for something like that, where there's a nice right angle between a smooth surface going along and up. OK, and finally, you will need some cooking oil. And also, if you don't have any of that, a bit of Vaseline. And there you go, that's all you need. So if you want to get those things together and then listen to what Hugh is about to tell us what to do. So Hugh, what do we do with these things, firstly?
Well, it's interesting. If you just take your ball and roll it towards the wall, it bounces back. But I wonder whether you've really thought about how it bounces back. Because if you imagine that as it rolls towards the wall, it's rolling clockwise, if we call that clockwise, but when it's coming back, it's got to be rolling anti-clockwise.
OK, so, shall we get Martin and James to kind of have a go at that and see what they see? Who's up first? We've got some bouncy balls here. Martin, you're going to have a go. So basically, we want you to roll the ball just along the horizontal surface so that it hits the vertical wall and then comes back, and then basically tell us what you see. So go for it.
Okay.
OK, so what did you see that time? It was rolling quite gently there.
I saw the ball when it was going towards the wall, spinning clockwise, and then it came back when it hit the wall, going anti-clockwise.
Well, OK, it's absolutely right. It changed its direction of spin. But did you notice it was bouncing at all when it came off the wall?
It starts bouncing after it hit the wall when it's coming back.
Yeah, that's right. So it seemed to get a kind of a kick upwards just at the moment that it kind of hit the wall. So what's going on there, Hugh?
Well, it's very important that there is a kick upwards, because the ball has to change its direction of rolling it from going clockwise, as it were, to going anti-clockwise. And it's only the kick of the wall that can do that. And the kick of the wall has to be upwards to make it change its rolling direction. It then bounces a few times and it gets a few more kicks from the floor, but the very first kick it gets is an upwards kick from the wall. OK,
so the way the ball was rolling as it kind of approached that vertical wall meant that it tried to roll up the wall. That was the direction of it rolling, but of course gravity means it can't really do that, so it just kind of gets that slight kick upwards, but it's also bounced against the wall, so it's coming back, and then eventually it starts rolling back the other way. OK then, now we've seen that effect, but what is it we would like people at home to try now?
Well, what's interesting is that if we were to put a bit of oil or grease on the wall, where the ball is going to hit the wall, so just rub it on with your finger, then essentially we're making the wall slippery, which means it can't get that kick up the wall anymore. So the question is, will the ball roll back off the wall faster or slower
OK, so we're going to make a slippery wall. Now, James here has been kind of standing patiently watching Martin do all the rolling. But what do you think is going to happen? Is the ball going to come back faster or slower?
Well, I reckon it's going to come back a bit faster because it's just going to grip to the ball a bit more, and I think it'll just slide off, as it were.
All right, OK. Of course, you at home, we'd like you to try this as well. I don't know what you think's going to happen, but, it might surprise you. So please do. And if you tell us the right result, then you can win a prize from The Naked Scientist. So the number to call is 08459 25 2000, and you can also email chris@thenakedscientist.com. And we'll be back here at the Norwich School anyway, later in the show, to find out what actually happens, and also an explanation from Hugh Hunt here. So until then, from James Martin and myself and Hugh, it's goodbye and back to you.
Thanks, Derek. So just in case you missed any of that, all you need to do is to get hold of a bouncy ball, roll it up against the wall, and see how far back it comes. Then you do the experiment again, but you put a little bit of oil on the wall, just make sure it's a tiled surface, not your mum's favourite wallpaper. Does the ball come back faster or slower than before? What do you think the answer is going to be? Helen?
And yep, don't forget, we're also asking you our teaser question, which this week is, what metallic chemical do we need in our diets to make sure we have enough red blood cells? Now, we're getting lots of callers. Thank you ever so much. Lots of you are along the right lines. We've got Sybil in Sawston, Andre in Cambridge, Margaret in Peterborough, Miriam in Wyndham. You're all along the right lines. But I'm afraid, Hazel, you got it a bit wrong. It isn't zinc. Now, do phone in. We're still waiting for your calls, 08459 25 2000, or text us on 07786 20 1960.
You can, of course, email me, chris@nakedscientist.com. And remember, we're collecting questions because coming up very shortly, we'll be talking with Nick Sarkis and Ron Douglas. Now, Nick Sarkis is a consultant ophthalmologist. He operates on people's eyes for a living. It's what he does for a profession, so he's an expert on how the eye actually works and how to put it right when it goes wrong. Any questions on that for him? And Ron Douglas works on the science of vision and how the retina processes light signals and turns them into things the brain can understand. So any questions for those two, same numbers, 08459 25 2000.
The Naked Scientists. Supported by the Wellcome Trust.
It is The Naked Scientists. Dr. Chris, that's me, and Dr. Helen, and we're taking your questions about anything to do with vision, and that's in a second, because first of all, general question from Peter, who is in Godmanchester. Hello, Peter.
Hello. Yes, there's a well-known brand of washing powder is recommending that we start washing clothes at 30 degrees centigrade instead of 40 degrees centigrade. Well, I can see the energy benefits of that, but what bothers me is that a certain amount of the odour with clothes and so on is bacteriologically, is caused bacteriologically. And is 30 degrees actually hot enough to kill the majority of bacteria in the wash?
That's a really good point. There's a few things to bear in mind with this. The smells that you get on clothes aren't actually the bacteria themselves per se. What happens is that your body creates the ideal home for bacteria to live in the groin, under the arms. The bacteria live on dead skin and sweat that you squirt out onto the body surface. This means they flourish in those sites. They produce trace elements and chemicals and various metabolites which soak up into your clothes like blotting paper, and they're a bit whiffy. So that's why clothes smell a bit. It's not necessarily because they're contaminated. But then when you wash them, of course, you wash out those substances, and that's why you restore that very nice smell to them, and often you put fabric softener in, which smells good too. But, and you've made a very good point, are actually these temperatures sufficient to neutralise any bacteria that might be on the clothing? And this could be important if you're, say, working in a hospital, I suppose, couldn't it? So you've gone to work in a hospital and you've been in contact with bugs that are on people. Would washing your clothes at a lower temperature be bacteriologically safe? Well, the answer is that there's a lot of detergents in washing powder, and it's very, very alkaline as well, in fact. It can cause caustic burns if you put it on the skin. So it's a pretty harsh environment, and you would take some pretty hardy bugs to survive it. But some can, and things like mycobacteria that can cause TB can survive in those conditions. So it would have to be a pretty hardy bug, which some could argue deserves a chance at life if it can survive the kind of conditions you'd see inside a washing machine. But no, it's true. You maybe should consider heating washing up if you think there's a risk. There could be some bugs loitering on there.
Yes, it's just a point that has been glossed over, I think. Nobody's really raised it, so I thought it was worth raising it. Incidentally, if it's as alkaline as that, presumably you do really need a good thorough rinse as well. Otherwise, if there's any trace of the washing powder left behind you can get problems with your skin.
Oh, you can. And what people sometimes do is they think, I'll get some washing powder, I'll put it in the bath and just do a hand wash. And if you're not careful, your skin will begin to fall off in layers because the sodium hydroxide type, sodium carbonate and that kind of chemical, they are very, very alkaline. It denatures proteins, in other words, makes the protein that makes the skin up fall to pieces. And it can be very, very irritating and effectively causes a chemical burn burn. I did actually see a case once of a little boy who'd got into the cupboard and got hold of some dishwasher powder. And dishwasher powder is very similar to washing powder, actually. They're pretty similar. You can put washing powder in the dishwasher if you get desperate, and I've done that before. But this little boy had opened the can of dishwasher powder and tipped it down his front, and it had gone inside his nappy. Mixed with the water, the dampness in the nappy, it then formed this obviously very, very corrosive solution and caused third-degree burns to his lower abdomen and to pelvic region.
Ouch, that sounds...
So you have to be very careful. Never get this stuff in your eye, because, the guys this evening can tell us about chemical burns to eyes. I'm sure we can ask them in just a second. You can very quickly damage your eye extremely severely with, especially alkalis, getting onto the surface of the eye.
I can believe that, yes.
Do you want to go at the quiz?
Oh, yes, please.
The coldest place on Earth is the North Pole in wintertime. Do you think that's science fact or science fiction?
I actually think it's fiction.
You're right, it's actually the other end of the planet, it's the Antarctica, with record lows of minus 91 degrees Celsius.
Well done, Peter. 1 out of 1 so far. Next question. The largest tree ever measured weighed over 3,600 tonnes. That's a lot, isn't it?
Ooh, 3,600 tonnes. I think that sounds just a little bit ambitious. No, I think that's false as well.
I'm afraid it's actually true. It was a giant coast redwood in 1905 that fell down, and it was 3,688 tonnes. Apparently could make over 5 billion matchsticks, but I'm not quite sure how we worked that one out.
Peter, thanks very much for your call.
Thank you.
The Naked Scientists, Chris and Helen, and we're taking your questions on anything science, but specifically with a slant towards vision this evening. If you'd like to join in, 08459 25 2000 is our phone number. Text in on 07786 20 1960 or email me, chris@nakedscientist.com.
And now we're going to hop across the pond for Bob and Chelsea's fishy update this week. Sounds like my kind of thing. They'll be telling us all about how lice are causing havoc in salmon farms and why we should watch our step next time you're in the ocean.
This week on Science Update, we're going to bring you the latest news about how salmon farms may be killing wild salmon. But first, in other fish news, Chelsea tells us that there may be a lot more venomous ones out there than anyone guessed.
When you think about venom, you probably think about snakes. And there are about 450 venomous snakes in the world. But a new study from New York's American Museum of Natural History shows there are at least 3 times as many venomous fish. That's at least 1,200 venomous fish in the world. Ichthyologists Leo Smith and Ward Wheeler made this estimate by placing the 200 previously known venomous fish on their new evolutionary tree and guessing which other fish species would also have venom. They then confirmed their predictions with dissections. Smith explains that this estimate is very conservative.
Only when someone had actually published a paper talking about venom in a group did I include them. And, plenty of us have been stung by other ones that are clearly venomous.
Smith says he wouldn't be surprised if the number rises to over 6,000. Important news for drug researchers who often use venoms to develop new medicines.
Thanks, Chelsea. A salmon farm can indirectly kill young wild salmon within a 35-mile radius. This according to a 2-year study of over 14,000 fish led by PhD student Martin Krakosik at the University of Alberta in Canada. He explains that salmon farms are teeming with sea lice, a parasite that's relatively harmless to adult salmon but deadly to juveniles.
These fish are only about an inch long. They weigh about half a gram. They don't have any protective scales, and all it takes is 1 or 2 lice to kill them.
In the wild, juveniles rarely get sea lice because they grow up far away from adult carriers. But Krakosik found that fish farms along juvenile migration routes can infect and kill up to 95% of the young fish that pass by. As a result, he says that farming appears to be depleting the wild salmon population rather than saving it.
Thanks, Bob. That's it for this week. Next time, we'll talk about some prairie dogs who are too busy thinking about you-know-what to look out for predators. Until then, I'm Chelsea Wald.
Sex, right? They're thinking about sex?
Yeah.
Thought so. I'm Bob Hirschon for AAAS, the Science Society. Back to you, Naked Scientists.
Thanks, guys. And if you want to hear more from the team at Science Update, you can go to their website, www, as they say in the States, www.scienceupdate.com.
Laying the facts bare, the Naked Scientists.
We're talking this week about the science of eyes, the science of vision, the science of sight, and how to put it right when it goes wrong. And to kick off the game this evening is Nick Sarkis, who's a consultant ophthalmologist at Adam Brooks Hospital. Thanks for joining us, Nick.
Good evening.
So, eyes must be the sight we all value more than anything, I would think.
Yes, I think people do value their sight enormously, highly.
But how does it actually work?
How does sight work?
How does your eye actually work?
Well, it converts light into chemical energy and then into electrical energy, and that's transmitted via the nerve to the specialised cells in the brain.
OK, but obviously the environment's full of light. How does it actually end up getting to the right place in the eye? What's going on at the front?
It has to be focused. So the front part of the eye is concerned with focusing it correctly onto the retina. And the retina is very highly specialised to receive the light and convert it into the chemical energy.
OK, but what about the fact that I reckon about half the population probably wear glasses? Why is that? Why have we ended up with a problem with our eyes that we need glasses?
Good question, and it's very disturbing, particularly apparently to the Chinese and the Asian groups of people, that myopia, which is the inability to focus light accurately on the retina because the eye's too big, seems to be increasing. And the question is why?
OK, but what's actually going on in the eye when someone's either short or long-sighted? What's the problem?
Well, the problem is that the retina is not quite at the right focal length for the refraction of the eye. If they're short-sighted, the retina's too far back, and if they're long-sighted, the retina's too far forward, as it were.
OK, so if we actually turn to how the eye can actually go wrong, there must be lots and lots of diseases that cause eye problems, which get worse as we get older, apart from just short and long sight.
Yeah, lots of diseases. The three most common, and the commonest worldwide, which is curable, is cataract. And that's still the commonest cause of blindness worldwide.
So what's going on in someone with a cataract?
In cataract, it's the lens which has become cloudy. Now, the crystalline lens within the eye is designed to remain transparent, but as it ages, it tends to change its chemical structure so that it's no longer transparent.
It becomes foggy.
Exactly.
So do we know why that happens?
We know why it happens in some people with rare metabolic conditions. We don't exactly understand why it happens to everybody eventually.
Is it a familial thing? Does it tend to run in families?
It can run in families. That's unusual, but it certainly can do.
So, obviously it's pretty routine to put it right now, isn't it?
It's become probably the most common operation that's done worldwide, yes, to remove the crystalline lens and replace it with an artificial lens.
How do you actually do it?
Well, with some high-tech equipment in the Western world, but it can be done much more simply without the high-tech equipment. It tends to be done like that in many other countries in the world.
So go on, Nick, talk us through the actual nuts and bolts of what's involved in doing a cataract operation, because there are probably lots of people who've been told they have an early stage of cataract, because it's not an all-or-nothing thing, is it? I mean, some people have a bit of cataract change, and it's not sufficient that they need it replaced there and then, but they will do one day. So what are they going to be facing in the future?
Well, they're going to be facing an operation where the lens is removed and replaced with an artificial lens. Now, in order to do that, we have to make an incision into the eye. So it's a major operation. It's not a trivial operation. And that's why it's not carried out unless the cataract is causing the individual trouble. Trouble of one sort or another. Perhaps they can't read very well, or they can't recognise their friends across the street, or they're having difficulty driving, particularly at night, because of the glare.
So you make a small incision in the side of the iris, the coloured bit?
Make a small incision into the eye, and then with an ultrasound device nowadays in this country, we soften the hard part of the lens, that's the nucleus, suck it out, and then suck out the surrounding part of the lens called the soft lens matter, and then into the capsule where the lens was, we insert an artificial lens.
So, correct me if I'm wrong, but we have muscles in the eye that either stretch or compress the lens to get it fatter or thinner so that it focuses light on the retina when it's working properly. So does your implant, the artificial lens you put in, have that capability or not?
Not yet. There are attempts to try to design material and a lens which will have some flexibility within the eye, but so far they're not very successful.
So does that mean that people who have this done do end up a bit short-sighted or a bit long-sighted as a result, and can that be corrected for?
Yes, they tend to resent. If they prefer, they can be long-sighted or they could be short-sighted. It depends on preference, really. Some people, having been short-sighted all their lives, would still like to remain short-sighted, and so we put a lens in which keeps them a little bit short-sighted so they can read unaided.
Got a question from Ralph, who's in Stamford, and he wants to know what's glaucoma.
Glaucoma is another important condition of ageing, really. It can occur in very, very small babies, but usually it tends to occur in older people, and it causes a gradual loss of peripheral vision, not central vision to begin with, but peripheral vision. Now, the reason that it's causing that is because the nerve is being gradually damaged, and usually the reason for that is that the pressure in the eye is too high. And the treatment that we can give to try to prevent this happening is treatment to lower the pressure, either with drops or sometimes with operations.
OK, Keith is in Peterborough, and coming up shortly we'll also be talking to Connor in Tillingham and Stephen Southwold, so hang on you two. But Keith's in Peterborough. Hello, Keith.
Good evening to you.
You wanted to talk about astigmatisms?
Yes, I'm very short-sighted, but over the years I now suffer from astigmatism. I'd like to know what it is and what causes it.
Well, the normal cornea is essentially...
That's a bit of the front of the eye, isn't it?
That's the front of the eye. It's essentially spherical. But if it's not quite spherical, in other words, if it's not shaped like a football, but like a rugby ball, it creates astigmatism, so that the eye doesn't see perfectly in all planes.
Does that help, Keith?
Yes, it does, because I'm noticing that my lenses are getting thicker and thicker, especially towards the edges.
Yes. Your spectacle lenses?
Yes.
Yes.
Because I think the analogy, because I have an astigmatism, the analogy the optician used with me, Nick, was a rugby ball-shaped eyeball. Right. Is it actually the eyeball that's off, or is it just specifically the cornea?
It's usually just the cornea, but it can be also contributed to by the lens, by the crystalline lens.
But does this run in families?
Can do, yes, and there are certain diseases which produce it. There's an unusual disease called keratoconus, which is a disease of the cornea, a kind of malshapement of the cornea, which causes astigmatism.
Quick go at the quiz for you, Keith?
Yes, I'd like to have a go, please.
OK, the average sneeze travels about 100 miles an hour. Do you think that's true or false?
I think that's true.
Yes, that's absolutely right. About 10 metres in a quarter of a second. It can travel a total of 9 metres and dispense 100,000 virus particles. Lovely.
Next question, well done, Keith. An elephant's heart beats about 50 times every minute. Fact or fiction?
I think that's fiction.
It's much slower than that, you're right. It's about 30 beats a minute, which is much slower than us people.
Well done, Keith. 2 out of 2. You're in the lead at the moment. Thanks for joining us on The Naked Scientist.
Thank you. Goodbye.
Sorting out the sparks from the quarks. The Naked Scientists.
Connor's with us now. Hello, Connor.
Hello.
Thank you for joining us. You're in Tillingham. What do you want to talk to Nick about?
Yes, I've got diabetic retinopathy in both eyes, and I was wondering if there's any evidence that if you get your sugar levels just right, the blood vessels would repair themselves.
Nick, what do you think?
I'm not sure whether they can repair themselves, but what seems to be the case is that if you keep your blood sugar very well controlled, the chance that you will develop severe diabetic retinopathy is reduced. So it's well worth trying to keep your diabetes extremely well controlled.
So you can stop it getting worse rather than actually reverse the damage you already have.
Exactly.
But there's some evidence that that people like you can play a role in that, aren't there, Nick, by actually stopping these blood vessels that are doing nasty things in the retina from getting worse?
Well, quite, yes, because once the blood vessels have started proliferating in the retina, then we know that if they can be lasered with a very high energy laser, and they can be destroyed, and that prevents them causing the damage which they would otherwise cause to the retinal function.
Does that help you, Steve?
Well, it does a way, but I've had 4 lots of laser treatment, and it hasn't really done any good.
So I guess it's a question of stopping it getting any worse rather than actually trying to reverse at the moment what you can do. Do you want a quick go at the quiz?
Yes, please.
A rocket that has to reach over 40,000 kilometres per hour to escape from Earth's gravity. Do you think that's science fact or science fiction?
Fact.
That's absolutely right, yes. A very fast escape velocity indeed.
The chance of winning the National Lottery jackpot is 50 million to 1. Fact or fiction?
Fact.
I'm afraid it's a slightly better chance than that. Just a little bit over 13 million to 1. So it's not quite that bad.
1 out of 2, Connor. You're in second place.
OK, then.
Thanks for joining us on The Naked Scientist.
Bye-bye.
Do you have any questions for us about the science of sight? 08459 25 2000, email chris@nakedscientist.com or text in on 07786 20 1960. Steve's in Southwold. Hello, Steve.
Good evening, Chris.
Welcome to the show. What would you like to talk about?
It's a slightly unusual question I'd like to ask Nick is why cannot I recognise a face that I've known for many years upside down?
I have the same problem. I've seen this. When you turn a picture upside down, the face looks totally different to you, and it's much more difficult to recognise. Nick, do you have a clue?
No.
Ron, any ideas?
Not really. All I can say is that although we can't do it, and other animals like sheep and cows also can't recognise other sheep and cows when they're upside down, monkeys can actually do it. So it would seem to imply that if you habitually hang upside down, then it's something you can do.
So I've got to go batty then?
I guess so.
Sounds great. Yeah, I think bats could do it too, couldn't they?
What's the point? Has anyone actually looked at bats, Ron?
They've looked at bat vision, but they haven't looked at bat face recognition as far as I know.
Would you like to go at the quiz, Steve?
Yes, please, I'd love to.
The sun is now more than 25% hotter than it was when the Earth first formed. Is that science fact or science fiction?
That's science fiction.
I'm afraid it's actually true. Over the last 4.5 billion years, it has got a lot hotter.
Oh, good grief.
One more go. The fastest dinosaurs could run at 80 kilometres an hour. That's fast, isn't it?
That is fast, but I could run at 81 kilometres an hour, so I reckon that's science fiction.
It's true, actually. Ornithomimus was built a bit like a modern ostrich, 3.5 metres long, and can manage 70 kilometres an hour. Great.
Oh, thank you.
Thank you for joining us on the show.
Thank you. Bye-bye.
It is Chris and Helen, and we are, of course, talking about the science of sight. And Ron Douglas is here with us from City University. Hi, Ron. Thanks for coming along.
Hello.
Mentioning there, talking about bats and sheep and things. How do you know that sheep can recognise pictures of other sheep upside down, or not, as the case may be?
Well, Helen was explaining some experiments earlier on about pandas, how they could see colour. There are many things you can do. I mean, you can look at the structure of the eye, for instance, and that will actually tell you quite a lot about what the animal can see. You can also train it to do things. So in Helen's case, you were training it to distinguish a red target from different greys. You can, for instance, if you put an animal inside a rotating drum and there's stripes on the drum, they will tend to follow the stripes. It's called the optomotor response. And then you just make the stripes narrower and narrower until the animal no longer follows it. And then you can see how fine detail it can see. So you use various training techniques.
OK, well, let's sort of home in on your specialty, really, which is actually colour vision. There's an age-old question, which is that dogs can't see in colour. They have black and white vision, but it's not true, is it?
No, certainly almost all animals can see colour. There's very few that can't. I think possibly it's very difficult to imagine what the world looks like to everybody else. And we tend to think that humans probably see the world just about as well as you can. Now, it is true that humans are quite good at colour vision, and if you compare our colour vision to that of other mammals, such as dogs and cats, it's certainly better. But actually, mammals have fairly poor colour vision. Most mammals have what's known as two visual pigments, two types of cone. They are said to be dichromatic. They see the world rather like a red-green colour deficient person, whereas humans have three of these pigments, so they are trichromatic.
Is it because we go out in the daytime, Ron, that we have this intense colour vision?
It is, but actually our colour vision isn't that good when you look at outside of mammals. If you look at fish and you look at birds and you look at frogs, they actually have much better colour vision. They have more visual pigments, maybe 4 or 5, and they can distinguish a greater number of colours than humans can.
I think one of my favourite has to be the mantis shrimp that lives in the sea, and am I right in saying they're one of the most complex eyes out there? They've got 8 types of visual pigment, and then lots of other pigments for things like polarised light and distribution of light, and these fantastic stalked compound eyes. They're really great.
That's right. The mantis shrimp is, if you like, the world champion of colour vision. If you combine its visual pigments with the number of other filters it have in its eye, it can actually distinguish 16 different types of pigments within its eye, which compared to our 3 is really quite amazing.
It begs the question, why, Ron?
I think to humans, colour vision really isn't that important. I mean, I think if you said to somebody, well, you're going to lose your ability to see colour, they would be a bit worried, but it wouldn't be completely devastating, because our survival doesn't really depend and never has depended on our ability to see colour. In terms of evolution, it was quite useful for distinguishing green unripe berries and red ripe berries. It's a bit of a tongue twister. But if you compare that to, say, reef fish, which are so brightly coloured, colour is obviously much more significant in their lives than in ours.
How do we actually see colour, though? But I mean, how does the eye actually discriminate between colour vision and black and white?
Well, in order to see colour, you need to compare the output of 2 different types of cells, which are known as cones. Black and white vision relies on only one type of photoreceptor known as a rod. And because you've only got one type, you've got nothing to compare, so you can't see colour. But you can see colour by comparing the outputs of what in humans we call the red cone, the green cone, and the blue cone.
But this is very light-hungry, isn't it? So it doesn't work at night terribly well, which is that why we can only see sort of black and white at night? We don't tend to get colours very fiercely at night. We're not able to see them very well.
Well, if it's really quite dark and we're using only our rods, you can't see colour at all, no. That's because the ability to see colour and the ability to see at very low light levels, our so-called absolute sensitivity, are more or less mutually exclusive. So you either have to make the most use of the light or you have to be able to see colour, but you can't do both at once.
Got an email here from Jyotsna. I hope I've said your name correctly. Jyotsna says, why is it that we're perfectly comfortable with black and white movies and photographs when we know the real world's in colour, but the same picture in, say, a red or green or shades of any single colour doesn't seem to have the same satisfying effect, i.e. it's okay to replace a colour with a grey tone, but not shades of other colours?
I confess I don't really know the answer to that, but I suspect it's just what we're used to. I mean, we are used to seeing colour photographs, and we are used to seeing black and white photographs, and black and white TV and colour TV, but we're not really used to seeing red TV or green TV. I suspect it's just what we're familiar with.
Here's a question for you, Nick. It's Margie who's in Ilford, and she says her eyes often become watery for no apparent reason. Why do you think this is?
When you go out in the wind, it's a stimulus to tear production. Now, tears are quite useful because they keep the cornea, that's the front of the eye, moist, so that they keep the surface smooth, so that they keep the eye functional. But if you go out on a very windy day, often you produce a few too many tears, and they'd fill up the whole conjunctival sac, and so you're looking through water, and it's rather disturbing. So I suspect that's what it is. It's different conditions which will bring it on.
It's just an irritant response, essentially, then?
Usually, yes.
Ron, here's a question for you. It's from Winnipeg in California, actually. In Canada, sorry. Kerry Stevenson says, we all know that when we open our eyes underwater we see blurry images, and I believe this is because water has a different index of refraction from air, where our eyes have been designed to work properly in air, of course. My question is it possible for someone to have such poor eyesight in air that they'll be able to see clearly underwater?
The problem is that normally in air, light is focused by both the cornea at the front of the eye and the lens within the eye. And actually most of the focusing is done by the cornea. And the reason the cornea can focus is because the refractive index of air and water are different. Or air and aqueous humour, that's the liquid within the eye, are different. But as soon as you put your head underwater, the refractive index of the water and the liquid within the eye are the same, and the cornea no longer focuses the light. So the cornea is lost as a refractive surface. In answer to the question, our eye is said to have a focusing power of 60 diopters. 45 diopters is due to the cornea, so about 3/4 of the eye's focusing power is due to the cornea. When you go under the water, you lose the cornea as a focusing surface. So you would have to be 45 diopters myopic, so minus 45 diopters, which means normally you would be focused at just over 2 centimetres. I've never met anyone who's more minus 45 diopters myopic.
I think even Britney Spears is only about minus 10, and she has very bad eyes, so she had laser therapy to get her eyes right. Margaret's in Upminster. Hello, Margaret.
Good evening. Yes.
Thank you for joining us. What would you like to talk about?
Well, I have neovascular macular degeneration of the right eye, which means I've hardly any sight at all left in there. Well, I haven't any.
Yeah.
Well, when I went to see if I could have laser, and I was a bit of a guinea pig for an American thing done in Hillingdon Hospital to see if they could do something for it. Again, laser, nothing happened. But the very downside news was, this is going back 6 years ago, the surgeon said, well, there's a 40% chance you'll get in the other eye, and I mean, that's devastated me ever since.
So would you like to know from Nick basically what it is? Is that your question?
Well, yes, what the chances are. I mean, of it happening in the other eye.
OK, let's ask Nick. Nick, what do you think?
I can't give you an exact chance, really. This problem of neovascular degeneration of the retina, which is a devastating cause of visual loss, is due, we think, to some sort of metabolic fault in the retina, which allows blood vessels to grow into the retina and then distort the retina. Up until very recently, we hadn't got very good treatment for it, because laser treatment is quite destructive, and of course if you laser a retina, you're going to destroy the retina in the process. But there is some very exciting development, very exciting news, because there are now 2 new drugs which seem to be helpful in this condition. And so it's possible that in the future we're going to be able to treat people like you with this condition.
Thanks, Nick. Keep your calls coming in, 08459 25 2000, email chris@nakedscientist.com, or text in on 07786 20 1960. I'm going to very quickly squeeze in Jean, who wants to know about squints. Hello, Jean.
Hello.
Now, we're going to have to be really, really swift, so what was your question?
2nd of July, a husband developed squint overnight,
Yes.
double vision.
Right. Why is that? Nick, why is that?
Well, it's probably because one of the muscles is not working properly. Now, the muscles to the eye, there are 6 muscles, and it's probably because one of them, or perhaps 2 of them, are not working very well.
So it could be a nerve being pinched or something somewhere.
It could be due to that. It sounds as though, because it happened overnight, it's more likely that a blood vessel blocked, and so the supply of the nerve was damaged, and so the nerve doesn't work very well, and usually it will tend to recover within a few weeks.
It's reassuring news, Jean. We have to leave it there, but I hope that does give you some help.
OK, thanks.
Thank you for joining us.
Bye.
It is The Naked Scientists. Chris and Helen, we're talking about the science of sight, and I'm very quickly going to sneak in Les, who's in Peterborough. Hi, Les.
Hello, Chris.
What's your question?
Bulls seeing red.
Can they see red or not? Right, Ron, can bulls see red?
Yes, bulls can see red, but they probably can't distinguish it from green.
Why not?
Because they only have one visual pigment in that part of the spectrum.
And that means, in English?
That means that they can distinguish blue from other colours, but it means they can't distinguish red from green. They see the world like a red-green colour deficient person.
So waving a red rag at a bull is actually a bit of an urban legend?
Well, it's not a legend, because what they're responding to is the waving. They respond to motion rather than the colour. But they can still see the colour. They will just get confused between red and green.
Do you want a very quick go at the quiz, Les?
Yeah.
The temperature at the centre of the sun is about 1 million degrees Celsius. Is that science fact or science fiction?
That's science fiction.
Absolutely right. Well done.
And the next question, Les. The DNA in one of your cells, if unwound and stretched out in a very long straight line, would be about 2 metres long. Is that science fact or science fiction?
Fact.
And right again. Well done.
Well done, Les. 2 out of 2, and thanks for joining us.
OK, thank you.
Time now to head back for our Kitchen Science Part 2, because remember that Derek is at Norwich School with Hugh and Martin and James, and they've been bouncing balls around. Derek, what's you got for us?
Hello, welcome back to Norwich School. We're still here with Martin, James and, of course, Hugh Hunt, who's been setting up this experiment with some bouncy balls and rolling them up against a wall and so on. So here we go. We've actually managed to smear some oil now onto the bit of the wall where we're going to roll the ball onto. And so, Hugh, I wonder if you could just direct James here, who's ready with the bouncy ball, just tell him what to do.
OK, well, James, you had a go at rolling the ball towards the wall when it was nice and dry and clean. And now you've seen me smear some stuff on there. Now, you reckoned it was going to come back a bit faster. Why don't you roll the ball now and see what actually happens?
And tell us what you see.
Well, it's actually slowed down quite a bit. It hasn't actually got faster.
OK, and Martin, did you notice any difference as well?
Yes, I did, because when James did it there wasn't any bounce when it came back, when you just threw it, when there's oil on it.
Yeah, OK, so when it kind of hit that wall, it didn't actually have that upward kick as it bounced back towards us, away from the wall. So there we go. Not what we expected, I dare say. So, Hugh, what was going on there?
Yes, well, Derek, I think you just said it there, that when the wall was nice and dry, the ball was able to stick to it, and it rolled up the ball a bit and jumped up. But now it's slippery, the ball simply slips and cannot roll up the hill. But, more interestingly, is that it can't actually use the wall to change its spin direction. So it starts rolling back towards us after hitting the wall, spinning the wrong direction. So then it really has to rely on the tabletop to make it start to spin in the correct direction. And by the time it's spinning in the correct direction, it's lost all its energy and comes almost to a complete halt.
What we saw then is that in this experiment we've had two conditions, a dry wall and a wet wall. And so when we rolled this rubber ball at the dry wall, it actually got a kick because the direction that the ball was spinning meant that it actually bounced upwards slightly. And that helped it gain the other direction of spinning and actually roll back towards us quite quickly. However, when we put some oil on the wall, that meant that the wall was very slippery and the ball could not actually climb up the wall at all. It couldn't get that kick. And essentially it meant that the ball was still rolling forwards, even though it was actually trying to come backwards. And if it was rolling backwards, it would make it much quicker in doing so. So really then, we had a much slower ball rolling back towards us when the wall was slippery, which is not what we expected, actually. Now then, Hugh, what we want to know, of course, is do we see this kind of effect anywhere?
Well, yes, if you're interested in snooker or billiards, you'll find that you might expect the ball rolling towards a cushion to do exactly the same thing. But you might notice that the cushions are angled, and the point of contact between the ball and the cushion is actually not exactly halfway up the ball, but it's higher up the ball, which means the cushions are in fact designed especially so that the ball will not jump when the ball bounces back off the cushion. If the ball did jump, then that would be not very satisfactory in a game of snooker.
Yeah, absolutely. Have you ever noticed that, guys? On a pool table or a snooker table, the cushions are kind of sloped, almost over the ball as it bounces on them. So it means it's not quite like this, and so the ball doesn't jump. Ever seen that, Martin?
I have, yes, because when I went on holiday, there were some pool tables there, and we saw them that they weren't angled. And so we played, and then we saw the balls bouncing off the cushions.
Oh, so what, shoddy pool tables then, not correctly designed or something?
I think they were second-hand.
Oh, OK, fair enough. Well, there you go. Well, thanks anyway, guys, for doing the experiment with us. James, did you like the experiment?
Yep, I did.
OK, good stuff. And are you going to go and, get some hold of some second-hand pool tables now as well?
No, I've already got mine, so I don't need it.
OK, that's fine. Well, thank you very much anyway, and thanks to Hugh Hunt as well for doing the experiment. And that's all from Norwich School for this week. So until next time anyway, it's goodbye.
Thank you very much, Derek, and also to Hugh Hunt and Martin and James at Norwich School. Next time, Derek and Dave will be finding out about the balance and about how we balance, and they'll be playing around with some office chairs in Northamptonshire. So you need yourself one of those swivel chairs that you can spin round on if you want to take part in next week's Kitchen Science. Helen.
We've had lots of right answers to the teaser question. Thank you ever so much for all your calls and emails. It's Howard in Histon, you were right. Hazel in Folsom, Keith in Peterborough, Gwen in Huntingdon. But, of course, there can only be one winner, and that is Austin in Chelmsford. Thank you very much. You will be getting a copy of Naked Science, the latest book from the Naked Scientist from Chris. I've got a question here from Phil Warburton, who says, this is probably going to Ron, do birds that hunt in water or above water have Polaroid vision? Because wouldn't that be a great advantage for them to be able to see through the water?
In fact, a lot of animals have polarized vision. So that's actually a good suggestion. The other thing that I think is really interesting is that birds that actually dive under the water, because earlier on we were talking about the way that humans go long-sighted when they look underwater. Well, actually birds who dive underwater don't, because they can actually accommodate by up to 60 diopters. That is, they can really change the shape of their lens, which they do by ramming it up against a very solid iris, and they actually form a great big bulge on the front of their lens.
Good effort. That's amazing.
Absolutely amazing.
Graham in Norwich, very quickly for you, Ron, I think, says, why are the cones in our eyes red, green and blue? Why not red, yellow and blue? How can we see yellow?
They're not actually red, green and blue. That's what we tend to call them, but they're actually blue, green and yellow. The long wavelength cone absorbs mainly in the yellow, not in the red. So that's how we can see yellow.
Well, that's it for this week, and thank you very much, Ron Douglas from City University and Nick Sarkis from Addenbrooke's Hospital in Cambridge. Next time, we'll be exploring the science of sound, including how the ear works, how cochlear implants can restore hearing to people with deafness, how bats use ultrasound, and also how to build the perfect concert hall. So if you have any questions on any of those topics, please email them to me, chris@thenakedscientists.com. Also, for some other top science news, there's the Nature podcast, which you can find at nature.com/nature. And there's also my book, Naked Science, or The Naked Scientist, as it is in Australia. And that's available from all good bookshops, or you can get a copy through our website at thenakedscientists.com. Thanks for listening, and see you next week.